let's talk about equilibrium and how we quantify the equilibrium. So if we look at an equation, A plus 2B in equilibrium with C. Okay, doesn't matter so much which equation. What is important is that it's an equilibrium. We can always recognize it with the reversible reaction. Okay, so I'm not going to talk too much about the condition of the equilibrium, but the point of this it would be how to quantify it. So an equilibrium can be quantified with the equilibrium constant that is written as K with the small c, just because we're dealing with concentrations. In fact, there are other equilibrium constants that we will come across. But this one is the basic one. But actually, all of the equilibrium constants, they're always quantified as concentration of the products divided by the concentration of the reactants. The units of this Kc will depend on the products and the reactants, so of how many of this we have. What I mean is that the concentration, they have to be to the power of their stoichiometric coefficient, let's call it n. So for this specific equation, that Kc will be concentration of the product, which is concentration of C, divided by the concentration of the reactants, which is concentration of A and B, to the power of their balancing number, therefore will be 2, also called stoichiometric coefficient. So always products over reactants. And this is important to understand what the meaning of the number means, but to that a bit later. Now let's think about the units. So considering that it's all concentration, remember that the square bracket is the concentration. So it's the like mathematical symbol, let's say, for concentration. The unit of concentration, and I'm gonna write it as this, because if just giving it a letter makes it easier for us to work it out. This big M is also molar concentration. In fact, it would be mole per decimeters cube. This is because if we want to work out the units, we just needed to play around with them and cancel them out, because I'm going to rewrite this with that big M that is relative to the concentration unit of the products and reactants. So Kc will have one concentration unit at the top, 1 for A times by m to the power of 2 for B. Okay, because we have one concentration at the top, and then we can also rewrite this as we have a 3 at the bottom, so to the power of 3, because remember the rule of power, if we times them up together, is to the power of 3. And now we needed to cancel out considering their units, so they have the same meaning. This is just a little bit of algebra. This will cancel out with this one to the power of 2, and this becomes 1. So canceling out the unit, we have 1 divided by the concentration unit to the power of 2. Because it's a unit, we never leave it to the fraction, okay? But instead, to remove this dividing factor, we would take the reciprocal of it, so it would be to the minus 2. But m is not the full unit that we want to write down, because remember that the molar concentration is mole per decimeters cube. So what does that mean? Mole per decimeters cube to the power of minus 2. Which we need to extend, of course, so it would be mole minus 2, and dm has become by 6. Okay, so a bit of fractions and a bit of rule of powers here to know. It seems like a lot of steps. Obviously, you don't have to do this of like writing down the mole per decimeters cube as a big M. You can even work it out, but with the extended unit, or just by thinking how many quantities you have as a reactant and as a product. But I think it's just like that, it's make it easier. And then during an exam, I just think it's better to work out everything nice and clear just to avoid mistakes. So I'm going to put one more on the screen, and you have the chance to work it out, and then I will give you the solution. So let's say that we have another theoretical equation, 3a plus 1b to give, let's say, 3c. Okay, so I would like you to write down the Kc and work out the units of this Kc. So Kc, always products over reactants to the power of their stoichiometric coefficient, so concentration of C to the power of 3 divided by concentration of A to the power of 3 times by concentration of B. Okay, so doing the extended method, if we wanted to work out the units, I would write, instead of mole per decimeters cube, I would write the molar concentration symbol, which is that big M. So we would have M to the power of 3 at the top, because we have a concentration to the power of 3, divided by M to the power of 3 times by just 1M, that it's the unit of B. So simplifying this, the M to the power of 3 cancel out, leaves 1 over M, but we know that we don't want to keep the fraction, so we would take the power of -1. So what does this mean? We have this mole per decimeters cube, which is the unit of concentration, but is to the power of -1, as we've simplified it. So what does that become? It becomes mole to the -1, decimeter becomes positive. If you want to be really, really picky, the positive power normally goes at the front, so we could actually write it like this. Okay, the fast way would be, like, once you get a bit more confident, you can just check, okay, we have 3 units at the top. You can even just do it by looking at the KC. We have 3 units at the top and 4 at the bottom. So this leaves 1 over 1 unit of mole per decimeter cube. Yeah, so as you can see, it's something that can be easy to work out as well, just if you are able to visualize it. Okay, but in the doubt, then I think it's always better to take a little bit the longer route, but the one that is the safest, because you can always go back and double check that you did all the steps right. Okay, so that's the unit. Another part of case C that I think is relevant before you do calculations or anything is, and because in AS sometimes you have to do very simple calculations. It could be finding the concentration or determine the value of Kc when you're actually given all of the concentrations. But the thinking part would be understand what the Kc means. So as we said, is the concentration of the products divided by the concentration of the reactants. Concentration of, but the reactants. So if the Kc would be bigger than 1, this means that the power, so the number at the top is bigger than the number at the bottom. So this tells us that there is a greater concentration of the products compared to the reactants. So this tells us about the position of the equilibrium. In this case, the equilibrium will lie towards the product, so on the right-hand side. Okay, which means that if the equilibrium lies on the left-hand side of the equation, remembering that the equation is always reactants to product. Okay, so if the Kc has a value that is smaller than 1, this tells us that the denominator is bigger, so the concentration of the reactants is actually bigger than the products. So this tells us that the equilibrium lies towards the reactants, so on the left-hand side. And one more thing to think about, and this comes from the knowledge of the Le Chatelier principle, is that the only factors that affect the position of the equilibrium is the temperature. Because remember that an increase in temperature favors the endothermic side. So with this means that actually one reaction is occurring more than the other reaction. So this unbalances the amounts of product and reactants that are present, while a decrease in temperature would favor the exothermic reaction. So taking just that there's a absolute random equation here, let's assume that the forward reaction is endothermic. You will know because the delta H is given in the equation. If this reaction is endothermic, let's say that we increase, so let me remove this one very quickly. So let's say that we increase the concentration, no, we increase the temperature. It favors, as we know, the endothermic reaction. What is the direction of the endothermic reaction? Is towards the product. So if you have to think about what effect does that have on the Kc value, you need to think that, well, if equilibrium shifts towards the product, it means that the net effect is an increasing concentration of product. So it means that the top of, the denominator of this fraction increases, which means that the Kc value would also increase. Okay, so you really have to think about the very basic math of numerator, denominator of a fraction, which one increases, which one decreases. The thing to remember is that all of these K constants, they're affected just by the temperature, because pressure and concentration do affect the equilibrium, the position of equilibrium, because as we know, according to the Chatelet principle, the equilibrium will shift to counteract the change. But before that shift, a change has been applied. So for example, let me just clear up a little bit. If we have actually, let's just take the example we did up here about this A and B. So if we increase the concentration of A, for example, it means that there is an increase in the reactant value, right? In the bottom value here, yeah, or as just concentration value. But according to the Chatelet principle, the equilibrium shifted to counteract the change, so it would shift to the opposite side. So to decrease the concentration of AC would also increase, which the net effect would also be an increase of the product. So notice how the fraction, the ratio between them stays the same, so that product's reactant doesn't change. So that's why concentration and pressure do not change the value of Kc. It's only the temperature, because it affects the one value over, like one direction of the reaction over the other one. Okay, so to summarize, Kc units, we have to work it out by simplifying the units, and that they're different for each reaction depending on how many products and reactants they are, because remember that they're always their concentration to the power of the balancing number. And then in terms of value of Kc, it can tell us the position of the equilibrium. Sometimes you can see the Kc being equal to 1, which means that you have the same concentration of products and reactants. But that's that's also a possibility where the equilibrium is exactly in the middle, which I didn't mention before. And then the last thing that I mentioned about the analysis of Kc is that it is affected only by the changes in temperature, because it favors the forward or the backward reaction. I would say that's a nice wrap up of Kc before getting into detail about the calculations of Kc, which that would be an A-level topic. Apart from, I think, one example, that is AQA, that you have to do it now, but that will be for another time.